In this last lecture in the module, we consider Mars and the possibility of life on Mars. Speculation about life on Mars has been going on for a very long time. Percival Lowell, in the late 19th century, used his telescope out in the desert just north of us in Flagstaff to see the canals on Mars, and he inferred the existence of a dying Martian civilization. We know now that he was wrong. Those surface features are not as linear as he thought, and he was using wishful thinking in part. But he seeded the idea of Mars as a living planet. By the 1930s, we had the graphic science fiction and lurid illustrations of books by Edgar Rice Burroughs, postulating strange creatures and adventurers working on the surface of Mars, and seeding the public imagination with the idea of life on Mars. And that led seamlessly to the classic science fiction of the 1950s, Ray Bradbury and others. Just before the Second World War, a famous incident occurred where Orson Welles, the Wunderkind director, did a radio play based on H.G. Wells' book from 1895. And in this radio evocation of the book, he scared the local populace with the idea of Martians landing on the Earth with ill intent. People were ready to believe it then. This moved seamlessly into the classic science fiction of Ray Bradbury and others in the 1950s. So as we reach the modern era, people have been primed for the idea of life on Mars for a long time. When the first pictures came back from Mars by the first orbiters and landers in the 1960s and 70s, it was a disappointment. Mars appeared to be an arid desert. So the idea of life on Mars has oscillated between, yes, it's got to exist and it's there already, and it has ill intent, to no, it's a barren desert. The pendulum has swung back to the possibility that there is indeed life on Mars, but microbial life. What do we know about Mars? Quite a lot, as one of our nearest neighbors in space. Mars is smaller and less massive than the Earth, and orbiting 50% further away in distance from the Sun, it's colder. The atmosphere is very thin, 1% of the density of the Earth's atmosphere, and it's almost entirely carbon dioxide. Combined with the very cold surface temperatures, that makes it impossible for liquid water to exist on the surface of Mars. Most of the surface of Mars is old and has not been resurfaced by recent volcanic activity. However, in more detail, Mars is interesting. It has weather, it has a hydrological cycle, though a mild one, it has prior volcanism, and it has plate tectonics in its past. We can see here animations from one of the landers in a time-lapse of dust devils on the surface of Mars. The dust storms, of course, scale up to dust storms that sometimes cover a good fraction of the planet. We can see large geological features. We can see ice caps on Mars that contain not only frozen carbon dioxide or dry ice, but also frozen water mixed in. So Mars is interesting, looked at in a bit more detail. And radar observations made from orbit starting a few decades ago show that pure ice glaciers exist covered by a few meter rocks. These pictures of the mid-latitude of Mars show through radar below the surface icy material, frozen and trapped in the rock. And this is common at the mid-latitudes. The rock protects the ice from subliming in Mars' cold and dry climate. These debris-covered glaciers are common at mid-latitudes, and the thickness of the ice is substantial. Some estimates say that if that mid-latitude ice were melted and deposited around the surface, it would cover the entire planet with 20 centimeters deep of water. The evidence for water on Mars is strong and varied, but indirect. Some of the evidence have other explanations, and there's no water visible now, but taken together they're compelling. Many of the surface features to a geologist represent the idea of ancient water flows or sedimentation. And as we've had landers to examine the rocks in detail, we know that sedimentary rocks exist on Mars. Perhaps the most exciting indication of potential biology, although there's no unique explanation yet, is Martian methane. Remember that methane is a greenhouse gas on the Earth produced almost entirely by biological organisms. Methane gas was detected and has been for over a decade in the Martian atmosphere using ground-based telescopes and more recently by orbiting spacecraft. The amount of methane is tiny, a few parts per billion, and the distribution is patchy. But intriguingly, it changes with time. It changes on timescales of weeks or months. The reason that's interesting is because methane degrades and is disassociated in the Martian radiation environment quite rapidly, so it will disappear. And therefore, if it's changing in its location and has a short lifetime, it must be being resupplied continuously. So since methane is produced by life on Earth, that raises natural questions about its origin on Mars, especially the fact of its variability. Geologists have suggested that this methane could be produced by geochemical processes without biology involved, and there's a vigorous debate in the planetary science community about the origin of the methane, and more data is still needed. But as I said, the methane would be destroyed by ultraviolet light within a few centuries, so it must have been produced recently. And variation suggests that it was produced in very localized regions, which also may be consistent with biology rather than geology. So Mars is a little more dynamic than we would suspect of what is now a geologically dead planet. Models suggest that the methane is produced at the interface between water and rocks. Now on the Earth, that methane could be produced at a water-rock interface by bacteria, and so we know of a mechanism that involves biology. So this is one of the most fascinating aspects of Mars that we still don't fully understand. Mars has been the commonplace for missions in the last few decades. As almost our nearest neighbor, it's difficult to get to, hundreds of times further away than the Moon, but you're working with a very fascinating place where the possibility of life is strong. And so missions over the last 50 years have tried to explore Mars. The most striking missions in terms of their success and their longevity were the Spirit and Opportunity rovers, which lasted many times more than their planned lifetimes of 3 months. One is still active, while Spirit died after getting bogged down in a sandbank. In fact, most of these rovers of some longevity have essentially worn out their scientific instruments and their wheels and their gears and their moving parts because they're so successful. These durable robots were the first objects we put on the surface of Mars that gave us an indication that there had been standing bodies of water in the distant past. A mission that was launched by NASA but controlled and operated by the University of Arizona and my colleagues was the Phoenix lander. It went to the polar region of Mars for 6 months in 2008, and it saw evidence of a hydrological cycle, which is to say that although liquid water cannot exist on the surface of Mars, if it's sufficiently briny, it actually can be a liquid. And so drops of briny water were seen on the legs of the lander, precipitating out of the thin Martian atmosphere. It also saw the chemical perchlorate, which is associated with some biological processes on the Earth. So that was another piece in the evidence that Mars could potentially be active. The current rover, Curiosity, is the next generation rover that's been working on Mars for several years, and a more advanced twin of it is scheduled to head for Mars in a couple of years. It has a sophisticated set of 12 instruments on board. It's not a life detection experiment. Its twin, to be launched in a few years, will have actual life detection. But once again, it has given us very solid evidence that liquid bodies of water survived on Mars, and that the acidity of the water was in an intermediate range potentially suitable for biology. We've also had time-lapse photographs of the surface of Mars showing the sudden appearance over the time of the orbiters of water runoff down slopes, probably from the eruption of water from subsurface aquifers running down a slope and then evaporating. So there is substantial evidence that water exists even now in subsurface aquifers, where of course it will be kept liquid by interior heating from the rock and by the pressure of rock and ice on top. Despite the enormous effort and complexity involved in launching interplanetary probes, the success rate of these missions is actually quite good. Trawling the information database of Wikipedia, because NASA doesn't actually pull together in a nice way, I composed these statistics showing the success rates of missions to the inner solar system since the beginning or the dawn of the space age. And you can see that the success rate of these complex, expensive, and difficult missions is now 90% or better. So we're learning an enormous amount about Mars, along with other objects in the inner solar system. Perhaps the most compelling target to look for life is Mars. Our neighboring planet is a lot smaller than the Earth, not geologically active, not able to hold a thick atmosphere. But the evidence that there was liquid water on the surface billions of years ago, that it was warmer and wetter in the past, is compelling. And there's also evidence that water exists even now, kept liquid in aquifers under the surface. The total inventory of water is quite substantial. Observations just in the last year have shown that there are lakes, subterranean lakes, in the polar regions. So with energy and liquid water, there's a possibility of microbial life on Mars. And a series of rovers and orbiters have allowed us to home in on the possibility of life. Hopefully this question will be resolved in the next decade.